So what do you think? We're going to drain water through a little valve, and you can see the valve in the bottom here for this tank. And there are 4 sedimentation tanks here. Each tank is a separate unit. So we're trying to drain one of those, like 1/4 of this whole unit through this valve. And I also show another view in the back here. And I'd like you to just like think about, based on what we learned so far, what do you think? Is this a problem where major losses dominate, minor losses dominate, or those two must be equal? And as a reminder, major losses is about shear on the wall. Minor losses are about flow expansions. Minor losses dominate, and I'm wondering how you think about this. How do you think about which ones dominate? Because this, like, the truth is, the answer could be, I need to go do some math, right? I need to do some calculations and check this out. So that's actually a really good answer, but I need to go do some math. And the question is, like, what would the math be that you would want to do quickly to figure this out? If we look at the 2 equations for minor loss and major loss, they're so similar. There's major loss, there's minor loss. So what are we actually comparing? Given that the velocities are the same in both of them, we're just comparing which is bigger, FL over D or KE. And if you knew which one was bigger, you know which one dominates. And then the question is, well, what's KE? So for this pipe, there had to be an entrance somewhere. There's an exit where it's just dumping out and all that energy is lost. And there's the valve, and there's going to be some losses through the valve. Net is that at least you lose all the energy coming out the end of the pipe. So that's a K of 1. And so the question is FL over D greater than 1? And so an interesting idea is that F is on the order of 0.02, so 1/50th. And that means that if L is more than 50 times greater than D, then major losses have a chance of dominating. But if FL over D is less than, if L over D is less than 50, then chances are minor losses dominate. Of course, you should know what the minor losses really are, but it takes a lot of length of pipe to get you the same thing as just the fact that the pipe is exiting into the atmosphere and you're losing all that energy. So good job on that. Here's another thing about using the energy equation, and it's a trick that's about thinking about how we apply the control surfaces in the energy equation. So here's a tank. It's got a little hose connected to it, a small diameter tube. And we'd like to know how much water is going to flow through that hose. So we're going to apply the energy equation, and we're hoping that we can figure something out from that. And so let's look at this. So let's try this case where we're going to put a control surface for our control volume right at the beginning of the pipe, and another one somewhere where I'd like to get the velocities to cancel out. Because see the problem? I'd like to know what the velocity is through this pipe. I'd like to know what the flow rate is. So I need to know what the velocity is. And in the energy equation, the velocity is showing up, and I'd like that to cancel out somehow, because I want to get the energy equation to give me the head loss so that I can use that in the Darcy-Weisbach or Hagen-Poiseuille equation to figure out what the flow rate is. So I'd like the velocities to cancel out in the energy equation. So how could I get the velocities to cancel out? Well, I could put the second control surface right there, right? And now V in is the same as V out. And so I can cancel all those things out, and I'm, oh shucks. What do I do about Pn? What's Pn? Well, you're most certainly very tempted to say, well, that's rho GH. I can just take the height of water, H, and multiply that times rho G, right? Doesn't that make sense? But there's an I gotcha here, because the pressure at that control surface is not just due to rho GH. The water is accelerating as it's going through that control surface. It's got some velocity, and that means that this isn't a statics problem. So we can't use rho GH, I'm sorry to report, to calculate the pressure at the control surface. You see how that problem evolved? I wanted to figure out the pressure at that control surface, and I don't know what it is because it's not a statics problem. I need to know what the velocity is through that control surface in order to figure out what the pressure. Oh, and which equation would I use? I could use Bernoulli equation, because it is an acceleration into that control surface, but I don't know V, and so my problem just got worse. Okay, so this was actually a really bad path. So somehow I selected the wrong control surfaces. Did you ever wonder about this in fluids? Like, did you get the sense that figuring out where to put the control surfaces was not easy? Anyway, let's try again. So that was fail. So let's add the tank to my control volume. So now I'm putting the surface at the top of the tank. And what this does is it makes V1 go to 0. It's a big tank, okay? Kind of like the lake. So then where can I put the out control surface so there's no velocity? And this is where we get yet another problem. So we're going to do a trick. We're going to add an imaginary water surface right there. And I'm going to say this water is flowing into the very top of a tank. And I'm going to put my control surface on top of that tank. Okay? I don't actually need the tank. I just needed a horizontal control surface. And now the velocity through that control surface is also 0. But now, what are the minor? So my energy equation is now easy to solve, and I'm going to get that the head loss is equal to the elevation difference, which I've shown there on the graph already, or in the drawing. And my control volume is all that stuff in blue. So now what's the minor losses? So we have our control volume equation, and we have a second set of equations, which is the Darcy-Weisbach equation that is dimensionally correct, but that and we also have the minor loss equation, where it's the sum of k times v squared over 2g, and then the total head loss comes from those two. So let's try this. We're going to cross out all the terms that we know. We're going to get delta z. Oh, this was stage 1. This is what happens if I draw the control surface vertical on the effluent line. You see that? If the effluent line has a vertical surface on it and the water is flowing through that surface, then I get delta z equals v squared over 2g plus head loss. And I don't get this beautiful equation for head loss. So what we do when we flip the control surface from here to here, what we've done is we've moved that v out into a k. That change in velocity that loss of kinetic energy becomes inside our control volume, because our control volume exit has 0 velocity. So the change in energy as the water is exiting the pipe and falling into this big lake or tank, that energy loss is inside my control volume. And so I need to add that K to my minor loss coefficient. And so that means that my minor loss coefficient increases by 1 because I have that K from losing all of that kinetic energy as the water exits the pipe. And in that case, delta Z is just equal to head loss. And I have these set of 3 equations, and I just have to remember that my exit loss goes in the minor loss equation as well. And that makes solving this kind of problem really, really easy. And that's something that we will do plenty of times in this course. That method is also described in the textbook. So here's a system in India where we're taking water from a well. There's a solar powered pump down in that well that's lifting the water up out of the well and all the way up into a water treatment plant that is sitting on top of a storage tank so that the water gets treated, then goes into the storage tank, and from there goes to the community, the village, with a piped water system. And the question for you is, will the pump be able to lift more water up to the tank if the vertical pipe, so the vertical pipe is the section running up the side of the tank. Will the pump be able to lift more water up to the tank if the vertical pipe is smaller in diameter? Yes or no? Here's one way to think about when Monroe poses a question like this, a way to think about it that will in general help you figure out the answer. And that is to be an extremist. Take Monroe's question and apply the most extreme option possible. So here I just said if the vertical pipe is smaller diameter, so make that smaller pipe really, really, really tiny. Would you change your answer now? Like I take that diameter and I drive it to 0. At some point, that pump's not going to be able to pump any water through that pipe. So what is the pump actually experience? So there's this common misunderstanding that the big pipe of water is somehow makes the pump struggle, but it doesn't. You could have the pump, you could have the tank extend all the way down to the ground and the pipe from the pump just go into the bottom of that tank. Would that be easier for the pump or harder for the pump? Do you get my new case? We have the tank. The elevated tank is no longer elevated. It's now sitting on the ground and it comes all the way down. And the pipe that's coming from the well just goes right into the bottom of that tank. Is that harder for the pump? And the answer is no, that's easier for the pump. So what is actually makes it hard for the pump? The pump is experiencing pressure. And where's the pressure coming from? There's 2 things that are causing the pump to experience pressure. One is the hydrostatic head, which is basically the elevation of water in the tank or at where it's entering into the water treatment plant at the top of that building to the level in the well. And that elevation difference between the top where the pipe discharges and the well is a pressure that the pump has to be able to provide or lift. And then there's one more source of pressure, and that is head loss. So any friction or expansion losses in the pipe also increase the pressure that the pump is experiencing. So if we make the vertical pipe smaller, the head loss in that vertical pipe increases and the pump experiences that as additional pressure that it has to overcome to push the flow through the pipe. So the answer is, the bigger the pipe, the more water the pump can pump through it. And the fact that there's this big column of water there, that's not a problem, because the pump isn't even aware of that big column of water. It just sees a pressure. Okay, I've said that enough times. And this comes from a question that students asked in previous years, and that is, how do you get water to go up through a tank by gravity? Like, we have a tank, and this happens in our sedimentation tank. It also happens in our flocculator, where the water is flowing up part of the time. So how do we get water to flow up by gravity? It seems like by gravity, water should always go down. So here's the problem. Water goes down this pipe, it goes across, it goes down through those little pipes, it ends up turning around and going back up, it goes through the plate settlers, and then eventually it enters little holes in that pipe and it leaves that pipe. So the question is, why did that happen? Why did the water go up? How did we convince, like, did we have a little therapy session with the water beforehand that we talked it and we coaxed it into being willing to go up? How do we pull this off? Okay, so let's take a simpler case. Here's a U-tube. You can think of this as the right side here is my little tank. How do I coax the water in that little tank on the right side to go up? So what happens next if at time zero, I take a picture, and this is what this U-tube looks like at time zero. And let's just suppose that I also took a measurement and velocity right at this moment was 0. Okay, this is possible. What happens next? They're going to even out, and they're going to even out by the one on the left is going to go down and the one on the right is going to go up. So we're going to get, but what, and why does this happen? So point 1 is right in the middle of the tube. And I said this was a statics problem because right at this moment, the velocity was 0. So let's see, is this really right? So point 1, the pressure is equal to rho g times h left, but it's also got to be equal to rho g times h right, which means that there's got to be 2 different pressures at point 1, and that can't be true. So actually, this is not a simple statics problem. We'd be violating the laws of physics because you can't have 2 pressures at one point. That's not possible. So this can't be a static situation. And what's happening is at this moment, the flow is accelerating. Yes, the velocity was 0, but it's actually accelerating. And we will eventually get to this equilibrium point, and maybe it'll actually slosh a few times before it actually gets here, but eventually we'd get here. So point was, water's going to go from the side of the tube that's higher. And we can apply that to this tank here, where see the blue lines show up? That's the water level in the inlet. And there's the water level in the outlet. And as long as the inlet is higher than the outlet, water is going to be pushed through this system. And the fact that it has to go up part of the time is irrelevant. Just like getting the water to go up on one side of the U-tube is easily done. The water doesn't care. It's trying to get the pressures to even out.